When you originally learn about circles, you would have thought of them as a geometric object. It will be a shape along with squares, rectangles, triangles, something you might find the circumference of or the area of the space inside. But if we define circles more carefully and we have a precise definition, we can describe them algebraically, put them on a set of axes, and then all of the things that we normally do with algebra, we can then apply to circles. They're a common enough shape, they appear everywhere because of their fundamental and very basic definition. A circle is the set of all points that are a fixed distance away from a given central point. So if we can describe that constraint using x's and y's, then we're sorted. We can do all kinds of things with them. Let's start with a few quick questions. These will lead on to what we're going to do with circles, but they require you to remember some of the skills from straight lines that we'll be using and relying on throughout this chapter. First, find the distance between a couple of points. Prove that both of these points are equidistant from a third point. Then we've got a point 6k, which is exactly 5 units away from another point, the point 21. You need to find the value of k. And lastly, a general point whose coordinates are x1, y1 is also 5 units away from 21. And the question is, can you use this information to form an equation linking x1 and y1? And a bonus question, can you plot the points involved in these 4 questions on a graph and see what you notice? So pause the video at this point, have a go at these 4 questions, work out your answers, put it on a graph, see where you think I'm going with this, and then unpause and we'll continue. Okay, for our first question, hopefully we're using Pythagoras. You may have written it out in full like this. You might have done something a bit more intuitive. From 2 to 5 is a gap of 3. From 1 to 5 is a gap of 4. So we need 3 squared plus 4 squared square rooted, and we get 5. It's actually the classic 3, 4, 5 triangle. For the next question, to prove that each of these points is the same distance from 2, 1, we need to find the distance from 2, 1. So from minus 3, 1 to 2, 1 is actually simpler than it might seem, because these points share the same y coordinate. They're at the same height, and minus 3, 1 is exactly 5 units to the left of the point 2, 1. So if you notice that and you explain it, then there's no need to apply Pythagoras theorem to this one. If you do apply Pythagoras, it still works. You'll just have a 0 squared to contend with in the middle. Minus 2, you will need to apply Pythagoras, but this one turns out is also 5 units away. For the third question, we have another point which is 5 units away from the point 2, 1, but this time there's a variable involved. We still set up the same kind of equation. We're still dealing with Pythagoras, so we can use the difference between the x coordinates, that's 6 and 2, and the difference between the y coordinates, k and 1. We can square those two things, add them together, and then square root the answer to get 5. Now, because we're trying to solve an equation to find k, we need to get rid of that square root. So the next step along this process is to square both sides of that equation. So 6 minus 2 is just 4, so we have 4 squared, and we've got k minus 1 squared. But instead of having a pesky square root over all of that stuff, we've squared both sides, and we have a 25 on the right-hand side as a result. Well, we can rearrange this, simplify, and calculate the value of k. We get 2 values of k, in fact, k equals 4 and k equals minus 2. We're going to see how those two things are relevant in just a moment. The final question is asking you to generate an equation linking x1 and y1. Given that we don't have enough information to find the values of x1 and y1, the best we can do is some kind of connection between them, some algebraic link. And we use exactly the same method we had before. If we calculate the distance between that general point with its unknown x and y coordinates and the point 2, 1, we can do that with Pythagoras. We know the answer would be 5 because we've been told it's 5 units away. If we square both sides, just like we did with the previous question, we'll get x1 minus 2 in a bracket squared and y1 minus 1 in a bracket squared equals 25. That is the kind of connection we're looking for. You might have gone further. You may have expanded out the brackets and written it in terms of x1 squared and y1 squared and some x1s and some y1s, and then perhaps group the numbers together. That's actually quite useful. It's something we'll come back to later, but this is sufficient and is probably the most elegant way of writing the connection between x1 and y1. Now, if you plotted the points, then this is what you should have. It may not look like anything much, but there is a common theme that's been running through all of these questions. Either I've told you that the points are 5 units away from the point 21, or you've calculated that they're 5 units away from the point 21. So it turns out all of them lie on a circle around that point. Not only that, but the question involving k, we can see those 2 points in red, 6, 4 and 6, -2. They both lie on the circle. And if you think about it, saying the point 6k is 5 units away from the point 21 essentially is the same as asking the question, where does the line x equals 6 cross the circle? And of course, there are 2 places where that happens. If you drive past a city on a motorway that goes, let's say, 3 miles away from the city, at some point you'll be 5 miles away from the city. And then at some later point, after you've gone even closer, you'll carry on driving and you'll be 5 miles away again. In this case, the line that you can imagine coming down here gets closer than 5 units away, gets to as close as 4 units away when we get to the point 61, for instance, but it will get further and further away again as it continues to go up. There are 2 places where it is exactly 5 units away. Now, we've been using Pythagoras to find the distance between points. Turns out we can define all the points on the circle just using that same idea, Pythagoras theorem. So we pick this random point. And what's important about this is that this point could be any point on the circle. The only thing I'm going to assume about it is that it lies on the circle. And the definition of a circle is the set of points that lie a fixed distance away from the center. Now, in this particular diagram, I'm using what's known as a unit circle, which is just a fancy way of saying it has a radius of 1. So if my point has the general coordinates x1, y1, they just stand for particular constants that I don't know, I don't care, but they describe for me the x and y coordinates of a particular point that's on the circle. I also know that the x coordinate must correspond to the distance along from the origin, which is also the center of my circle. The y coordinate must correspond to the distance up from the origin. And because this is a unit circle, the other thing that we know for sure is that the distance away from the center is 1. And once we've got that, well, this equation jumps out at us. We've got a right-angled triangle, and we know that a squared add b squared equals c squared. Not only that, but because every single point on the circle satisfies this same condition, and no other points do, that description that we've got in algebra is a perfect description of every point on the circle. It is essentially the equation of the circle. Generally, we use variables for that. So we can think of any x value, we can substitute it into the equation. We will either get a solution for y, in fact we'll get possibly 2 solutions, because there are 2 valid y coordinates for any valid x coordinate on a circle, or we might get no solutions because there are no points of the circle that have that particular x coordinate. If you think about it, for a circle, there are going to be values of x that are too big. In this particular circle, if you try substituting a value for x that's bigger than 1 or smaller than -1, there won't be any valid solutions for y, because you'll end up with y squared equals a negative number. If, however, you put in a value of x that is between 1 and -1, there'll be 2 different values of y that satisfy the equation. So here's a bit of an animation to demonstrate this point. There are lots and lots of solution pairs to this. We can have points like √2 over 2, √2 over 2, where both x and y are approximately 0.7, or we can have 0.8 and 0.6. That works nicely because it's effectively a scaled down version of a 3, 4, 5 triangle. We can have 0.6 and 0.8. We can have pretty much anything else in between, as long as the two numbers square and add up to give 1, so the sum of their squares is 1, then any combination along there will work. But the only way that can happen is if we lie on the circle, because the one constant thing within all of those right angle triangles that you can see is the length of the hypotenuse. Coming back briefly to the question we had before, the circle from the last slide. If we have a particular point x1, y1, in this case, we get something slightly different, and that's because this circle is not centered at the origin, and also this circle doesn't have a radius of 1. But that doesn't stop us using Pythagoras. We can still identify within that circle the right-angled triangle. We just have to be a little bit careful when we're calculating the lengths of the sides of this right-angled triangle. It's no longer useful to compare the point on the circle to the origin, because there's no rule that says it's got to be the same distance from the origin. In fact, you can see points like -2, -2 are quite close to the origin compared to points like 5, 5. But every point on the circle is the same distance from the center of the circle. And in this case, the center of the circle is the point 2, 1. So we need the length of the purple arrow and the length of the red arrow. And we'd like them in terms of the coordinates of the point x1 and y1. Well, the purple arrow goes from the point 2, 1 to the point x1, y1. And that means that its distance is going to be equal to x1 minus 2. This is because the x-coordinate of the point in question is all the way along x1 units to the right of the origin. But the center is already 2 units to the right of the origin, so we need to subtract 2 to figure out what the difference is, how much further along we need to go. And a similar thing happens in the y direction. We have y1 minus 1, because the y-coordinate gives us the distance from the origin, or effectively how far up from the x-axis. In this case, that's going to be a negative number. So it might help you to think in terms of concrete values. If we imagine x1 as 5 and y1 as -3, -3 take away 1 is 4, which is the actual distance there. And 5 take away 2 is 3. So we can see the 3, 4, 5 triangle appearing again. And in fact, because the distance from the center to every single point is 5, we can fill in that line as well. But the key thing here is that this method for calculating the length of the two shorter legs of the right-angled triangle, that will work no matter where you are in the circle. If you're not convinced, pick one of the other points that's got numbers and try applying the same rule, x1 minus 2, y1 minus 1. And you should find that in every case, that gives you the horizontal distance from the center and the vertical distance from the center. Now, if we square the two shorter legs of the triangle and we add those things together, Pythagoras tells us that we should get the square of the hypotenuse. So this is the equation of this circle. And you can see the connection with x squared add y squared equals 1. There's a bit of variation in there because instead of squaring x, we're squaring x minus 2. It's like a translated version. And instead of squaring y, we're squaring y minus 1. Again, there's a translation involved in that. And then on the right-hand side, we'll have a number like 25 instead of the number 1. But that is related to a distortion, a stretch both in the x and y direction. You could think of it like that. And it means we can represent not just circles with a radius of 1 or circles centered at the origin, but we could use this to describe any circle centered anywhere with a radius of anything. Good trick to try here. See if you can put the coordinates of some random point that's in the circle into the equation of the circle. I would recommend you try this with the larger circle on the right, one with a center of 2, 1. So if we pick a point, for instance, like 1, 4, you could test the numbers 1 and 4 in here. You could put a 1 in instead of x, put a 4 in instead of y, and see what happens. See what kind of result you get. Now it's not on the circle, which means it won't satisfy that equation. You'll find that it isn't equal to 5 squared. But then maybe you try a different point. Maybe you try the point -2, 6. Substitute the values -2 and 6 into the left-hand side. That point is outside the circle, so again, it will not satisfy the equation. It won't be equal to 25. But think about what you do get. What is it equal to, and what does that tell you about the point that you've identified? We'll come back to that idea. The next thing I'd like to look at is the Circles toolkit. Here's a bunch of techniques that you'll need to make use of throughout the circles topic. Some of these things you'll have come across before in earlier chapters. In fact, I think pretty much all of them you've done a little bit of before, but you'll be making use of them in some specific ways while working with circles. So now we've looked in detail at what a circle looks like on a Cartesian grid on an XY coordinate system. You might have some idea of how and when you might use each of these key skills. I'd like you to pause the video and jot down what you think the relevance is of something like finding the midpoints, the midpoint of 2 points on a coordinate system, or finding the distance between one point and another point, perpendicular lines, what completing the square might have to do with circles, graph transformations and where they come in, and even using the discriminant for quadratics. Pause, write down what you can about how you think those are related, and then unpause, and we'll see how many of mine you agree with and whether you came up with anything else that might turn out to be useful. So for the first one, a classic use for midpoints is locating the center from the endpoints of a diameter. If I can tell you that the diameter of a circle goes from the point 37 to the point 9 minus 4, well, in order to find the center of the circle, all you need to do is find the midpoint of those two, because the diameter goes directly across the circle through the center, and the center will be in the middle of the diameter. The distance to a point, well, if I give you the center of a circle and a point on the circle, finding the distance between those two will tell you the radius of the circle. You can also use this idea if you're trying to figure out if a point is inside or outside a circle, directly by thinking about the center of the circle and its coordinates and the radius of the circle. If you know how far away you are from the center, you can compare that number to the radius of the circle. If you're more than 10 meters from the center of a circle and the circle has a radius of 8 meters, you're outside the circle. If you are 7 meters from the center and the circle has a radius of 8 meters, then you're inside the circle. So that's a nice comparison you can do, but you'll need to make use of Pythagoras to calculate the distance to the point. Perpendicular lines. This is a bit more subtle. But the tangent to a circle is parallel to the circle at the point when it touches. But that means that it is perpendicular to the radius of the circle at that point. You'll see more examples of this as we go through. You will have come across it when you looked at circle theorems way back when. But because we can relatively easily calculate things like the gradient of the line from the center to a particular point on a circle, we can make use of that idea and the fact that tangents are perpendicular to radii to work out things like the equation of a tangent to a circle. And there's an extra suggestion here. The perpendicular bisector of a chord goes through the center of a circle. This is a really powerful theorem, but it's really obvious when you think about it carefully enough. What it's saying is, if you have a circle and you draw a random line across it, so you cut the circle into two unequal pieces, like a badly sliced pizza, one single line straight through, you've got one little sliver and then one big chunk at the other side. Now, the line that you've drawn, if you can construct the perpendicular bisector, that's equivalent to finding a line of symmetry across the circle, so that the two chunks that you've now cut, each of them is cut into two identical pieces. Well, because that line is a line of symmetry for the circle, it must go through the center. And that is a really powerful method we can use if I know a couple of points that are on the circle, even if they're not either side of the center, even if they're not diameter endpoints like in the first point we made here. They could be any 2 points on the circle. And if I can find the equation of the perpendicular bisector between those points, then I've got the equation of a line that definitely passes through the center. You might think that's not that helpful. You've got a line that goes through the center, but how does it help you find the center? Well, what if you had a third point and you could find the perpendicular bisector between points A and B and points B and C? Now you've got two lines, both of which definitely pass through the center, but they're probably not the same line because you've got three distinct points. So if you can find where those two lines cross, you've found the center of the circle. Completing the square. Turns out this is really helpful when you're rearranging different forms of the equation of a circle. You might remember that one of the circle equations you've already seen had something involving x in a bracket squared and something involving y in a bracket squared. So in some sense, the circle equation involves the completed square form of a quadratic in x and also the completed square form of a quadratic in y. So completing the square is a good way to convert something from a messy algebraic form to a format where you can easily identify the center and the radius of a circle. Graph transformations help us to understand what happens when we take a circle that is centered at the origin, let's say, and we move it so it's centered somewhere different. It's a quick, easy way to remember when you're looking at a general circle equation to identify where the center might be by thinking of it in terms of how you've moved it from one place to another. The discriminant relates to quadratics, and we are going to look at an example involving this shortly. But when we consider a line crossing a quadratic, we end up solving simultaneous equations, and we look at the discriminant to determine whether the line misses the quadratic entirely or just touches it at a single point at the tangent, or whether it crosses it twice. We can do exactly the same sort of thing with circles. We can find out if a line crosses, misses, or is tangent to a circle. And it turns out we get to use the same toolkit that we had for quadratics, because when you solve a line simultaneously with a circle, you end up with a quadratic equation all over again. Now, another thing you can do with this, which is a little bit sneakier, is to identify whether or not two circles intersect, and if so, how. Whether they just touch, whether they cross in two places, whether they don't cross at all. Circles crossing circles is a bit more subtle than lines crossing circles, and it's not necessarily something that you'll get into with the A level, but it would be worth investigating a little bit if you're curious and thinking about the different possible cases, because even if two circles never cross, that doesn't necessarily mean that the two disks don't intersect. Think about Venn diagrams, they overlap. Well, what if you had a very small circle that was completely enclosed within a larger circle? The two curves have no crossing points, and yet the smaller circle is somehow inside the larger circle. So depending on how you were interpreting this or what you were using this mathematical model for instance, a computer game where you've got objects that are intersecting one another, you need to know when a shot is on target, for instance, then you might need to consider how you would determine if one circle is overlapping another circle, including the case where one is completely inside the other one. Now, for each of these key techniques, there are questions that you can practice. For finding midpoints, the best ones are probably going to be within the circle equations chapter. So chapter 6, exercise 6A, questions 3 and 5. The distance to a point, if you want to recap doing this, you can turn to exercise 5G, the previous chapter, and try question 4. For perpendicular lines, come back to chapter 6 and have a go at question 3 from exercise 6B. If you need a bit of a reminder of completing the square, try question 6 from exercise 2E, way back in chapter 2 on quadratics, just so that you can build in some practice and refresh your memory on how to do that. Graph transformations, you can try question 3 from exercise 4G. We're now in chapter 4 on graphs. And finally, using the discriminant back in chapter 3, where we made use of the discriminant to determine whether or not a line and a curve crossed, or if they crossed, how. Repeated solutions, no solutions, etc. So try 3C question 7 for that one. Pause the video at this point, have a go at any of those questions that will be particularly useful for you. Especially make sure you try the ones from 6A and 6B because they relate directly to circles, but anything else you think you're a little rusty on, and you want to try one or two so that you can hit the ground running when you start the trickier circles questions, do those now as well. Okay, so now we can describe a circle algebraically. We can write the equation of a circle, not just some circles, but any circle you can imagine. We start with the most basic one, the unit circle centered at the origin, x squared add y squared equals 1. But then by scaling it up a bit, we get x squared add y squared equals r squared. All we need to do there is have a larger radius, and we say that the squares of the two shorter sides of that defining right-angled triangle add up to the square of the hypotenuse of that right-angled triangle. And if the hypotenuse is r, some radius other than 1, then we're going to get an r squared. The final version is a general circle. So it doesn't just have any radius you like, but it also has any center that you need. By translating your circle to the right A places and up B places, whatever A and B are, you can move the center to be any place you like, so that the entire circle is kind of focused around a different focal point. If x was equal to A and y was equal to B, then the left-hand side of the equation would be 0 add 0. That's the only way you can ever get 0 from the left-hand side, because x minus a squared is never negative, and y minus b squared is also never negative. So if you can make the left-hand side of this equation 0, it wouldn't satisfy the equation. The center of a circle is not on the circle, it's inside the circle, but it will give you the smallest possible value for the left-hand side. In other words, it's about as far in the circle as you can be. And incidentally, if you pick another point that's in the circle and you try substituting the values of x and y into the left-hand side of the equation when it's in this form, if it's in the circle, you'll get a value that's smaller than r squared. And if it's outside the circle, it'll be a value that's bigger than r squared. It's effectively telling you how far away the point that you've got the coordinates of is from the center of the circle that you care about. And if that distance is less than your radius, then it's within the circle that you're talking about. And if it isn't, then it isn't. Now, quadratic equations come in many different forms. They can be fully expanded, ax squared plus bx plus c. They might be factorized into double brackets. They might even be in completed square form. So the next question we want to investigate is, could we rewrite circle equations in different formats? And the obvious thing to try here is to take the general circle formula with its squared brackets and expand everything to get rid of the brackets. So this is what I'd like you to have a go at. Start by using the general circle formula to create the equation of this circle, a circle with center 3 minus 2 and radius root 7. Then I want you to expand the brackets so that we get something which involves x squareds, x's, y squareds, y's, and numbers. And then the final part, using the expression you've created and perhaps making use of the discriminant, see if you can prove that the circle never crosses the y-axis. And you might want to try again investigating what happens when you pick a point that you expect to be in the circle, pick a point that's outside the circle, and see what you get when you substitute that into the left-hand side. Try it with the expanded version that you generate in the second question. Once you've done this, unpause the video. We'll continue. So this is what your circle equation should look like initially. Take care with your negatives. If the x coordinate of the center is 3, we need the bracket with the x in it to say x minus 3. But then the y bracket is y minus the y coordinate. In this case, y minus negative 2. So it ends up being y plus 2 in a bracket squared. And then because the radius is squared on the right-hand side, we have root 7 squared, which is 7. Now, when you expand out those brackets for the second part, you should get this. If you look carefully, we've got x squared minus 6x add 9. That's this bracket. We have y squared add 4y add 4. That's this bracket. And then the 7 is unchanged at the end. But of course, we can simplify a little bit, because although the x's and y's don't mix and the x squareds and the y squareds don't mix, we can combine the numbers and we end up with this: x squared minus 6x plus y squared plus 4y plus 6 equals 0. Prove that the circle never crosses the y-axis. Well, a good way to start is to ask yourself what it would mean if it did cross the y-axis. So in this case, crossing the y-axis, as is the case with any equation that you're trying to identify y crossing points for, we set x equal to 0. We see when x is simultaneously equal to 0 and also the curve equation holds true. Well, if x is 0, then x squared minus 6x disappears and we're left with just the rest of the equation. Y squared add 4y add 6 equals 0. But we're not trying to solve this, we're trying to demonstrate that it has no solutions. So the simplest way to do that, instead of scratching your head and trying to factorize, which is a thankless task because it won't, and instead of attempting to use the formula or completing the square or even throwing it into the calculator, because none of those things will prove that it doesn't have solutions, you'll just fail to find them. What you need to do, unless you're clever with completing the square, where you can demonstrate from it that you cannot solve the equation, the simplest way to do it is with the discriminant. Calculate b squared minus 4ac. You don't even need to simplify it fully, you just need to demonstrate that it's negative. As soon as you can show that the discriminant is negative, that proves that there are no solutions. If there are no solutions to that equation, then there is no place where the circle crosses the y-axis. Now, that's not the only way you could prove this particular thing. You could, for instance, if you've got a decent diagram, you could see fairly easily that a circle with center 3 minus 2, with a radius as small as root 7, is never going to reach as far left as the y-axis. This is why a diagram is often a really helpful thing to have. Even if you might need to create a rigorous proof involving algebra, having the diagram will help convince you of what the simplest method would be to go about doing that proof. And in this case, it might have been sufficient just to note that the square root of 7 is less than the square root of 9, so it must be smaller than 3. Even I don't know the square root of 7 off the top of my head, but it's somewhere between 2 and 3, and that's good enough for the following line of reasoning. The central point, 3 minus 2, is 3 units to the right of the y-axis. So even the most extreme leftmost point of the circle is still going to be a positive x coordinate, because the radius of the circle is only 2 point something. 3 take away root 7 is positive, and that's the x coordinate of the leftmost point of the circle. And if the circle never goes further left than that, then it certainly never crosses the y-axis. So we can write circles in an expanded form. However, it's usually more helpful, particularly if we're trying to visualize or sketch these circles or solve geometric problems involving them. It's more helpful to have a format where we can immediately read off the center of the circle and the radius of the circle. We want to see the little a, the little b, and the r as numbers, so we can say this circle has a center of such and such and a radius of so and so. So is there a way to go from the expanded form back into the squared bracket form? Well, yes, there is. We're going to work through this example so that you can see how it's done. And in this particular case, the y squared bit is already kind of sorted out for us. There's an x squared add 5x that we need to deal with, but there's no pesky y term. So this one's slightly simpler even than most that you will end up doing. But it helps to illustrate the point quite well for us. The first thing we're going to do is recognize that if you have x squared add something x, and you want it to look like x minus something in a bracket squared, the process you're following is completing the square. Yes, there'll be some extra number bits that come out as a result, but they can be dealt with. They can be subtracted from both sides of the equation, so they get shunted across to the right-hand side. And in fact, in the case of this equation, those numbers will be what form the square of the radius. We've got a 0 on the right-hand side right now. That doesn't mean the radius is 0. That means when we complete the square, some numbers will appear on the right-hand side, and that will tell me what the square of the radius is. So we complete the square, with this section of the equation. And if we had any y's, we would complete the square with the y squareds and the y's as well, separately. So we get the completed square form of the x and x squared bits, and we'll get the completed square form for the y and y squared bits. A bonus question to try while we're working through this. Can you show that the point minus 2, 2 lies inside the circle? And if you can, see how many different ways you can come up with to explain or justify your claim that minus 2, 2 lies inside this circle. Okay, so this is what it looks like when we complete the square. I've kept things in terms of top-heavy fractions rather than decimals, because although it may look a little messier, it's a lot easier to work with. 5 over 2 can easily be squared. We just get 5 squared over 2 squared. So writing things in fractional form is helpful for that. Remember that the y part has already been written in completed square form effectively. Trivially, it's y minus nothing squared, take away nothing. But the x bit in completed square form is this. And we can see that the entire thing can be turned into the standard format simply by adding 25 over 4 to each side. So this is now the standard format for our circle. We can identify in there the 5 over 2, the plus 5 over 2 that corresponds to the minus a. There's essentially a y minus nothing lurking in there, which corresponds to the y minus b. And finally, 25 over 4 must be r squared. Not r, remember, but r squared. So if you can interpret those carefully, you can find the center, minus 5 over 2, 0, and we can get the radius by square rooting 25 over 4. Well, that gets us right back to 5 over 2, or, for simplicity's sake, 2.5. Now, for part B, it says write down the equation of both of the tangents to the circle which pass through the point 0, 2.5. And the bit that should jump out at you here, as you get more practice with this, is the phrase write down. If an exam question says write down or state, it's usually a suggestion that what you're about to do shouldn't take a massive quantity of work. It might be something you have to think hard about, but it's not something that will require lots and lots of tedious algebraic manipulation. In many cases, it's possible just to write it without doing any written work at all. You write your solution and no working out. It's possible to see the answer by thinking and not necessarily by doing lots of grunt work and pages of algebraic manipulation and so on. But in a question like this, if you've not already sketched the circle, then you should. It's going to make a big difference if you can see what you're dealing with. This is one of the big breakthroughs that Descartes gave us when he came up with the Cartesian coordinate system, x and y. He was lying in his bed staring at a fly that was buzzing around the room and thinking idly about whether there was a mathematical way of describing uniquely the position of the fly in three-dimensional space at any given moment. And he came up with the idea of how far from the floor, how far from the left-hand wall, and how far from the back wall. And out pops x, y, z for our three-dimensional coordinate system. And it has meant that we can now deal with problems that the ancient Greeks, genius scholars and mathematicians that they were, really struggled to solve because they were working purely geometrically. They had all sorts of sophisticated and clever and ingenious proofs, but we have what is effectively a super tool when it comes to working with shapes. If we can describe them algebraically, we can hit them with all the toolkit of our algebraic equation solving mathematics. And we can do that here, but we need to remember that sometimes there are elegant geometrical approaches that will save you a lot of time. In this case, if you look carefully at the point in question, the point 0, 2.5, and you think about the circle we're dealing with, I've marked the center on minus 2.5, 0, and remember the radius is also 2.5, which means the circle passes through the point 0, 0. And we can verify that by looking at the very first equation that was written for us up here, x squared add 5x and y squared equals 0. If we put 0 in as x, then we'll find that y has to be 0. Or equivalently, if you put 0 in for y, we find that x has to be either 0 or minus 5. So we can very quickly sketch our circle even just by using those techniques. But once we know where the circle is, not only do we know where it crosses the x and y axes, but we also have some sense of where the highest and lowest points are. Often when I sketch a circle, the first thing I put down is the central point. The next thing I put down are the extremes, left, right, top, and bottom. Because that gives me a sense of where it should be, and because I'm not brilliant at sketching circles, so if at least I know where the top and bottom, left and right are supposed to be, I've got a fighting chance of getting it right. Now, if you know where the top is and where the right-hand side is, this next point will not come as a surprise to you. That point happens to be exactly in line with the top of the circle, following a horizontal line, and with the right-hand side of the circle following a vertical line. And that means those lines are tangents. We've got the vertical line, which is the y-axis, x equals 0, and we've got a horizontal line, which matches up to the y-intercept 2.5. There they are. Those dotted lines give me the tangents at that point. No heavy lifting required. There are ways of finding the tangents to a circle from any point. Most of them are fairly tedious, and they will involve working with simultaneous equations and dealing with the discriminant. But in this case, we can see it more easily because we've got a diagram that helps us to understand how that point is special and unique for this particular situation. The last thing to point out, the point minus 2, 2 lies inside the circle. It certainly looks like it does from my picture. Given that the point minus 2.5 is the center, it's going to be pretty close, comfortably inside the circle. Some methods you might have used to determine whether or not it's in the circle. One of them might just be this rough and ready, here's a diagram, it kind of looks like it's in the circle method. And that's probably enough to convince you, but it may not be enough to convince a skeptic. There are all sorts of things that you might think are true from a badly drawn diagram that then turn out to be false. So one other way you could do it is quite simply to use Pythagoras and find the distance between the point minus 2, 2 and the center of the circle. If that distance turns out to be less than 2.5, then the point must lie inside the circle, because the circle is the set of points that are exactly 2.5 units away from the center, and anything less than that must therefore be within the circle. Another way to do it will be to substitute the values minus 2 and 2 into one of our circle equations. We could do it either into this one or into our completed square version, whichever one you feel most comfortable with. But what you'll find is, whichever one you substitute it into, when you put those numbers into the left-hand side of the equation, where the x and y reside, we should get a number which is smaller than the number on the right-hand side. In the case of the original version of the equation here, we'll get a value which is actually negative, because the number on the right-hand side there doesn't directly correspond to the radius. It's related to the radius. It's related more precisely to the square of the radius, but it's not exactly the same. However, if we get a number that's lower than whatever number is on the right-hand side, we know we're in the circle, and if we get a number that's larger, we know we're outside. If we sub it into the left-hand side of this equation, well, all we're doing really is finding the distance from that point to the point minus 2.5, 0. The only difference is we're finding the square of that distance, and we're comparing it to the square of the radius. So it comes to the same sort of thing, but either way, you can use the equations or you can use a direct distance calculation to determine whether that point lies in the circle. Now you can have a go at 3 or 4 questions from exercise 6C, questions 9, 11, 12, and 13. Next, circles are in some sense quadratic equations. They're not quadratics in the usual meaning of the word. When we talk about quadratics, we're usually referring to one variable quadratics. These are two variable quadratics because they do have powers of x that go up to but no more than x squared. So they have x to the 0 terms, like constants. They have x to the 1 terms, just x terms, and they have x squared terms. But because they're circles, they also have y terms and y squared terms. And that means that in some ways they're the same as quadratics. In other ways, they will be a little bit different. So we can't treat them quite the same, but we will find that a lot of the techniques we've learned for quadratics also apply in some form to circles. We've already seen how we complete the square. We just look separately at the x squared and x bit and the y squared and y bit, and we can complete the square with those sections and get a different format for the circle equation. Well, it turns out we can solve simultaneous equations involving a line and a circle in just the same way that we solve simultaneous equations involving a line and a parabola, like y equals x squared. So here's an example. We've got a couple of parts to this, so we're going to focus on the bit that's not grayed out to start with. Circle C has equation x squared add 2x add y squared add 8y equals -4. Sketch the circle, giving the exact coordinates of any points where it cuts the coordinate axes. Now, if you need to sketch a circle, the best way to do it is to start out by figuring out where the center is and what the radius would be. It's very hard to sketch a circle just by knowing its x and y axes crossing points. It's possible that it doesn't even have any, because it could be a circle that doesn't cross the x or the y axis. It might be that it has two, but it never crosses, say, the x-axis, just the y-axis. And it's hard to get an accurate picture of a circle if you've only got a bit of information like that. But every circle has a center and every circle has a radius. So the first thing I'm going to do is complete the square so that I can turn the circle equation into the standard format. This is a relatively quick process. You're completing the square. It's something we know how to do. So we take the bit that involves x, the x squared and the 2x, and we complete the square with that. Then we take the bit that involves y squared add 8y, and we complete the square with that. And then all we need to do is notice which bits are combinable. We can put all the numbers together, throw them all onto the other side. When we do that, we have x add 1 squared add y add 4 squared equals 13. And now we just have to interpret those values. Remember, the formula is x minus a in a bracket squared plus y minus b squared equals r squared. So one common mistake is for people to forget that this is the square of the radius. Our radius is not going to be 13, it's going to be the square root of 13. But another common mistake is, especially if both brackets have a positive in them, is to just look at the brackets and think, oh, the center is 1, 4. You've got to watch out for your signs. The center here is -1, -4. Another way to think of it is, these are the values that would make those squared brackets 0, because it's the point that it has the smallest distance from the point -1, -4. It is the center, it is that point, so the distance from it is nothing. Whereas the distance from it of any point on the circle is going to be root 13. Now we can find out where it crosses the x-axis by setting y equal to 0. You can do this in either the original equation or in our equation. If you put it in our equation, you'll already be partway to a solution through the completed square method. You can just continue to rearrange till you find x. But you might find it simplest just to put it back into the original equation. You'll end up with a quadratic, and you can solve that quadratic in any way you like. I believe for this particular one, I was quite lazy and I put it into the calculator. Be careful with that equals -4. Before you put it in the calculator, think of it as x squared add 2x add 4 equals 0. But you can put your 1, 2, 4 into the calculator, and when it comes out with some weird numbers that involve something plus something I, that's a clue that there are no real number solutions. You have to move into the complex number realm with imaginary numbers in order to find anything that will work in this equation. You can't square things to get negatives, and you can't square a number, add two lots to the number, and ever get an answer of -4, as long as the number you're dealing with is an ordinary real number. So there are no solutions to that, which basically means it doesn't cross the x-axis. Then we can see where it might cross the y-axis by setting x equal to 0. And we get this. The solutions are a bit messy looking, and I'd recommend you press the SD button so you can see roughly what size these are. But we need the exact values when we sketch our graph. So once you know which one is which and how big they are, then you can draw your graph. It doesn't have to be massively pretty, but it does need to show roughly where the center is and it needs to illustrate the fact that it doesn't cross the x-axis because there were no real solutions, but it does cross the y-axis, and we need to show where it crosses the y-axis. So at the top there, minus 4 plus 2 root 3, which is nearly 0 but still a little bit below, and minus 4 minus 2 root 3, which is almost negative 8. For the next part of this question, determine the values of k for which y equals x plus k cuts the circle at two distinct points. This is getting to be a slightly more meaty question. We're trying to figure out what k needs to be for this particular straight line to cross the circle at all. We're not saying here's a straight line, find out where it crosses. We're the next level up from that and saying here's a whole family of possible straight lines. Yeah, they all have a gradient 1, but you're allowed to move them up and down as far as you like. They will cross the y-axis at some arbitrary point, and we're wondering what kind of points they would need to cross the y-axis in order to intersect with our circle. The first thing I'm going to do is write down the two equations because I'm interested in where they may cross and whether they cross at all and for what values of k they cross. And I start as if I'm solving simultaneously. So we've got y equals x plus k. Everywhere I can see y in my original equation, I'm going to swap it out for x plus k. So if there's 8 y's, I'm going to have 8 lots of x plus k. If there's a y squared, I'll have x add k squared. And all of a sudden, we've got a quadratic equation on our hands. And this now should feel very similar to what you would have done in the quadratics chapter, solving simultaneously a straight line and a quadratic. We've got to expand out those terms. So here we've got the x add k squared. Here we've got the 8 lots of x add k. And then we need to group things together. So be careful with this, take your time, and try to avoid making mistakes. First time I went through this, preparing this presentation, I lost a k squared along the way and was very confused at the end when I discovered that it was impossible for the line to ever cross the circle at two places. When I drew the pictures, it looked like it certainly should be possible, and when I did the algebra, it didn't work out. But that showed me there must have been a mistake somewhere, and that allows you to go back, to hunt for it, to find where the mistake happened, and then to fix it. So it's not the end of the world. It'll happen regularly, and it's something you want to be on the lookout for. But don't expect that you'll ever eliminate the mistakes. What you might get good at is finding them before someone else does. So now we've got something which is not only a quadratic involving x, but it's written in terms of something x squared plus something x plus something. So if you look carefully, it's effectively already in the ax squared plus bx. And we're not going to let the fact that it's got k's kicking around all over the place bother us. This is a quadratic involving x. The solutions to this quadratic, if we were interested in them, would tell us where the line crosses the circle. But we have a slightly next level question to ask. We're asking for what values of k does it even cross the circle? I'd like to know what k needs to be in order for this equation to have two distinct roots. If the line and the circle are going to cross twice, this quadratic needs to have two distinct solutions. And that means we're looking at a discriminant question. We need the quadratic to have two distinct roots. That means we need the discriminant to be greater than 0. And although the quadratic we were looking at has two different letters kicking around, x and k, when we start looking at its discriminant, suddenly there's only one letter involved. Everything in there is involving k. A, b, and c are the numbers that go in front of x squared x and the constant at the end. So now what we have is another quadratic, but this one is a quadratic that represents the discriminant of the quadratic we had before, which in turn represented the set of solutions to where does the circle cut the line, or where does the line cut the circle. We need to be careful simplifying this. One thing you could do here, if you look closely, you'll see to make my life easier for that first bracket, instead of expanding out 2k plus 10 in a bracket squared, I've pulled out 2 as a common factor, because 2k plus 10 is 2 lots of k plus 5. But be a little bit careful because we're squaring the whole lot of 2k plus 5, which means if you split it into two pieces that multiply together to make 2k plus 5, to make sure it's equal to the same thing, you need to square the 2 and the k plus 5. Once I do that, though, I notice that 4 is a common factor of all of the terms, or both terms effectively, on the left-hand side. So I can divide both sides by 4 and make my life a little bit simpler. Anything you can do to make it easier to combine things without making mistakes is worth a step to do. Now we need to expand out the squared bracket, and we need to expand out the rest. So the k plus 5 in a bracket squared becomes k squared plus 2 lots of 5k plus 5 squared. And then the rest works out to look like this. Minus 2k squared, minus 2 times 8k, and minus 2 times 4. When that gets simplified, it looks like this. And it's a negative quadratic expression, and we want to know when that negative quadratic will be greater than 0. This is where we draw a graph, and it does not need to be a particularly pretty graph. We can find critical values by throwing that into the calculator. It's not something that's worth spending any amount of time on. Just put the numbers -1, -6, positive 17 directly in the calculator. When you've got your critical values, you sketch a graph. A rough and ready graph. This one just illustrates the important points. It's got the critical values. One of them is -3 minus root 26, way down on the left. And one of them is -3 plus root 26. Remember, root 26 is going to be a little bit bigger than 5, so -3 plus 5-ish is going to be 2 and a bit. The other important thing that I've represented with my rough and ready sketch is that it's a negative quadratic, which means it has a maximum. It comes up and goes back down instead of coming down and going back up. And I want to know when this negative quadratic is greater than 0. Well, that happens in between the two critical values. It doesn't happen either side, it happens in between. So we care about the values of k that are above this lowest value and below this highest value. We actually want everything in between those two. And that is how we got our solution. Those are the values of k for which the line cuts the circle at two distinct points. Incidentally, if the question had asked for the values of k for which the line is a tangent, we can use practically the same method. If anything, it's a little easier because instead of solving a quadratic inequality, you'd be solving a quadratic equation. These two lines are the extreme ends of the range of values of k that we've just calculated. In fact, if we were to draw on a few lines that are valid, they will be lines like this, somewhere in between. These are all the values of k we're allowed. Everything from up here, crossing at almost 2, to down here, crossing at 8. If we go to the extremes, if we were to let k take the value of -3 minus root 26, or -3 plus root 26, we would no longer have two distinct solutions, but we would have exactly one solution. And that would make the line a tangent line. If, on the other hand, we go beyond, if we get a k value that's bigger than -3 plus root 26, or a k value that's lower than -3 minus root 26, then our line will not cross the circle at all. Now, there's a few more questions for you to try. These ones in exercise 6D, questions 5, 8, 9, and 12. Some will require a little bit of problem-solving prowess, and they will all involve various elements of the circles techniques that we've talked about during this video.